Mr. Chairman, ladies and gentlemen, good afternoon. I'm very glad to have this opportunity to attend the conference. My name is Sun Lingxin. The title of the paper I will be presenting is Learning to Optimize Computation Offloading Performance in Multi-Access Wireless Networks. My presentation will include these four parts. First, the background of our research. Second, the model we have proposed in the paper. Third, the proposed approach. Fourth, experiments and results. And the last, some conclusions we have got. In the first part, I'd like to introduce the background of our research. Mobile edge computing has been proven to be a promising technology to ease the tension between ever-increasing computing demands and resource-constrained mobile devices. In an MEC network, a computation task can either be proposed as the local device of a mobile user or offloaded to the edge server for remote execution. Strategic offloading not only significantly improves the quality of computation experience, but also potentially augments the capability of an MU for emerging resource-hungry applications. On one hand, the wireless networks are becoming heterogeneous. Wi-Fi has been emerging to complement the cellular connectivity. Most of the existing works concentrate on the computation offloading performance in cellular networks. Consider the marginal cost of cellular networks usage. The free Wi-Fi is beneficial for an MU from an economic point of view. Secondly, I'd like to introduce the model in our paper. As shown in the picture, we focus on a multi-access wireless network, where one base station and multiple Wi-Fi access points are connected to the edge server via high-speed wired links. The cellular connectivity is priced, while Wi-Fi is free to use. The whole service region is divided into a set of small locations, which are covered by the BS, where Wi-Fi connectivity and wireless charging are available in some of locations. We assume that the regions covered by different Wi-Fi APs are not adjacent to each other. The network operates over discrete epochs of equal duration. In this paper, we consider a representative MU that moves in the service region following a Markov mobility model. When moved to the locations covered by Wi-Fi, the MU can choose to offload a task using either cellular or Wi-Fi, and otherwise, cellular is the only option. Moreover, the MU can get charged through wireless charging when located in special charging areas. At the beginning of each epoch, task arrival at follows the Bernoulli distribution. Unarrived computation task can be proposed locally at the device of the MU or offloaded to the edge server for remote execution using cellular or Wi-Fi network depending on the location. Task continues to arrive, but if the MU doesn't have enough energy or the MEC server is occupied at this epoch, the task is unable to be handled. So a task queue is equipped at the MU to buffer the arrived but not yet computed tasks. Further, another queue is employed to store the energy units, which is denoted as execution 2. The MU can only be charged in a specific area, so the distribution of energy when handling proposing tasks is very important. When the MU decides to offload the computation task to the edge server for remote execution, the uplink date rate can be written as execution 3 or 4. The transmission rate of BS and Wi-Fi varies dynamically according to the following factors, where W is the bandwidth, I is the state of the channel, O is the inference power to the channel, while D is the task transmission delay. At each epoch, the MU is associated with the BS or one of the Wi-Fi APs based on the location as well as the computation offloading decision. We let F denote the association state of the MU, where F equals 0 indicates that the MU is associated with the BS, and F equals 1 indicates that the MU is associated with one of the Wi-Fi AP. When the association state of the MU changes, the handover delay is given by equation 8. As shown in equation 7, the sum of the computation delay is based on the transmission delay of the link method selected by the MU and the delay caused by switching connection states. Therefore, switching the link state of the MU needs to be carefully considered. Next, we move to the part of proposed approach. The technical challenges of designing a computation offloading policy lies in the network uncertainties due to the MU's mobility. The sporadic task arrives, the sparsely distributed Wi-Fi connectivity, and the intermittent wireless charging opportunities. Accordingly, we apply a Markov decision proposed framework to formulate the problem of computation offloading over the infinite discrete time horizon. The objective of the MU is to find a policy to minimize the expected long-term cost. The observed state consists of positions of the MU, the number of tasks in the queue, the channel states of the BS and Wi-Fi, the connected state, the energy queue, the task arrival indication. Based on the state, the agent makes joint decisions, including how the task is handled and how the energy is allocated. In order to consider the impact of different factors more comprehensively, the computation offloading cost of the MU consists of 3 components: transmission latency, payment, and the length of task queue. Our goal is to minimize long-term costs. Under an MDP framework, the optimal state value function satisfies the Biermann's optimality equation, but using dynamic programming to solve it faces problem of dependence on the state transition probability, which is infeasible in practice. We can notice that the number of state action pairs is huge in our computation offloading problem. Hence, the time cost for convergence is unacceptable due to the tabular nature in queue function updates. To address the challenge of a huge state space, we adopt a deep IL approach, DQNREG, to solve the optimal control policy for the computation offloading in multi-access wireless networks. Different from the DQN architecture, DQNREG adds a weighted Q value to the standard squared Biermann error when defining the loss function. Equations 16-17 represent the loss function and its update respectively. Okay, now we move to the part of experiments. In the experiment, we aim to compare the average performance from our approach with the 4 baselines by charting the energy arrival rate. The simulated performance in terms of average cost, average computation delay, average payment, and average queuing delay are depicted in 4 pictures. Picture 1 tells that our approach achieves better computation offloading performance compared with the 4 baselines, and the average cost keeps decreasing with the increase of the energy arrival rate. The reason is that more energy at the MU allows more arriving tasks to be computed with a low delay guarantee. Picture 3 and 4 exhibit that the average payment and average task queuing delay. This can be interrupted that the increase in available energy enables the MU to make use of any opportunities to compute the arriving tasks. Now we come to the last part, conclusion. In this paper, we concentrate on investigating strategic computation offloading to minimize the expected long-term cost for the MU in a multi-access wireless network. Taking into account the network uncertainties, we model the problem of computation offloading over the infinite discrete epochs as an MDP, the solving of which remains to be challenging. We explored the evolved DeepIL DQNIG for the first time to approach the optimal computation offloading policy under the constraints of no a priori knowledge of network uncertainty, statistics, and an extremely huge state space. The neural experiments demonstrate that our DQNIG approach outperforms the baselines in average cost performance, striking a baseline balance among the task computation delay, the payment for cellular connectivity, and the task queue delay. That's all for my presentation. If you have any question, please feel free to contact me. That's all. Thank you.